This video is meant to introduce you to some circuit physics. In particular, we're going to consider resistors in series, so purely resistors in series. This is as opposed to having resistors in parallel or mixtures of resistors in series and in parallel. And in order to do this, first, I just want to introduce you to simple circuit diagrams. So what's going on right now is we are taking a macroscopic point of view. Previously, in lectures previous to this video, we took actually something of a microscopic. That is, we were paying attention to individual charges and really small parts of materials. We thought about the sizes and shapes of the conductor materials and those materials' resistivities. And we were talking about electric fields and current densities and all of those things. And actually, we're going to stop and not talk about that stuff explicitly in this current material. So what you're going to learn in this video and subsequent lectures is more like just called circuit physics. Okay, so circuit physics, we're definitely going to talk about energy, but we're not necessarily going to talk about electric field. We're going to talk about current, but not really the current density, right? So we're going to take this sort of macroscopic point of view. So we're going to study currents, resistances in this particular lecture, resistances, and then voltages, right? Okay, so let's have some diagrams which tell us what circuit are we talking about. So the diagrams have parts. So here is something that you've seen before. This is meant to indicate a battery, right? And it goes without saying, so I'm going to probably stop saying it. It goes without saying that the long plate is meant to be the positive plate, right? And the short plate is the negative. So what that means, what you should assume, is that this is the high potential side of the battery, and this is the low. So you're supposed to assume those things. And now I'm going to take away all those things that you're supposed to automatically assume and just leave behind the battery, right? So you know which side of the battery is the higher potential side. Okay, so it's kind of funny to say this, but another piece of diagram is actually just the straight line. And this is meant to be a wire. And more than that, though, what's meant by this is we have an idealized perfect conductor with no resistance. So this is a wire, it's a perfect conductor, no resistance. But this right here is the circuit diagram for a resistor. All right, so we use wires to connect batteries to resistors. So here's a very simple diagram or a simple circuit. Here's a battery. I'll orient it this way. And I'm using a wire that's got two bends, right? One bend, a second bend, to go over to one side of a resistor. And then I use another wire to connect the other side of the resistor to the other side of the battery. So here is V and here is R. And remembering what I said, that the long plate is the positive plate, what's going to happen in this circuit is the conventional current is going to flow this way. And it's flowing in that sense everywhere around the circuit, all at the same time. So when this corner of the circuit has the current I flowing around it, at the same time, this corner of the circuit also has I, and down the resistor also has the current I, and along this lower leg of this lower wire, also current I. Around this corner, current I. The current I is the same everywhere at the same time. All right, so let me remove some of those. It's getting kind of busy in there. Right, so the current is flowing in a clockwise sense. Right, so sometimes this is given a symbol that looks like that. Right, so it's going around in this sense, clockwise, right? Counterclockwise is the other cycling sense. But anyways, this is the conventional current. We can use Ohm's law, right? Let's say that we know, let's give the voltage a value, 10 volts, and let's say that the resistance in the circuit right here, over here, this is often actually called the load. It's the load for the power supply. And this load, let's give it a resistance of 20 ohms. So what we can find out is, for example, we can use Ohm's law, right? Ohm's law says that the current is the voltage divided by the resistance. So this one's pretty easy to do, right? We're given the voltage and the resistance. It's sort of the first thing you can solve for. So if we go ahead and finish this out, you got 10 over 20, which is 1/2, and then volts per ohm, but the volt per ohm is the amp, right? So that you're given, it's the current is 0.5 amps. But another thing we can calculate is the power dissipated at the resistor, right? So this is the dissipated heating, or the Joule heating at the resistor. Remember, it's I squared R, and I squared, right? So half squared is 1/4, right? So that's 1/4 amps squared. And then the resistance, R, is 20 ohms. We're calculating a power. We're using SI units. So whatever we calculate, right, 20 divided by 4 is 5. Amps squared times the ohm is equal to the watt, right? So 5 watts of power dissipated by R. What's the power at the battery, right? What's the rate at which the battery is supplying energy? The equation that we use there is we just take the current and multiply by the voltage of that battery. And the current is, once again, it's 1/2 amp. And the voltage is 20 ohms. I mean, sorry, 10 volts, excuse me. The voltage is 10 volts, and 1/2 of 10 is 5, and the amp times the volt is also the watt. And we had to have this, right? Because the physics, if you think about this, we understand how the battery can lose energy because it's providing it to the rest of the circuit. And we understand how the resistor is dissipating the energy as heat. So we lose energy at the battery, we throw energy out of the resistor via heating, and there is no other mechanism in this physics problem for energy to show up or disappear, right? So we had to have that whatever power was being used up at the battery, it was coming out of the resistor. This is energy conservation. Right? That's an energy conservation statement. So that's the simple circuit. Now, though, let's move up and talk about series circuits. So let me draw you a diagram of a series circuit. I'm going to draw it kind of in a funny way. I'm going to say that the battery is up here, and it's oriented this way. And over here is a resistor, and it's got a resistor value R1. And then down here is another resistor, and it's connected to the battery by a third wire. So very quickly, I'd like you to notice that there's actually 3 different conductors right now. Here is one conductor. Here's another conductor, right? That is, it's one of those perfect conducting wires. And here's the third conductor. Right? So I have 3 different conductors in this series circuit. Up here, though, I only had actually 2 conductors. I had this conductor up here, and I had this conductor down here. 2 conductors. And if I only have 2 conductors, then I only ever have one potential difference, because the lower conductor has one value of potential, and the upper conductor has another value of potential. And the difference in the potentials between the upper conductor and the lower conductor is maintained by the battery. That's the job of the battery. The battery holds the potential difference between the conductors it's connected to. But over here, what's interesting is the battery is maintaining a potential difference between the blue conductor and the red conductor. So we are guaranteed a certain potential difference between those 2 conductors. But the green conductor can have a potential value in between the blue and the red. It's going to have a value that's in between blue and red. So anyhow, let's put in some values. Let's say that the voltage is again a 10-volt battery, right? The battery's positive side is over here on the left-hand side. And actually, I'm going to ask you to just remember that that's how the battery is oriented. The battery is oriented this way, and the current that flows in the circuit flows according to our battery there. So it goes like this. So the current through resistor 1 is downwards, and the current through resistor 2 is towards the right, and the current along the blue conductor is heading this way. So the current is flowing. In this case, it's called counterclockwise, right? It looks like this as opposed to this. Cool. So check this out. I'm going to go and I'm going to start at the battery on the positive side, and I'm going to look at the conductor that it's connected to, and I'm going to say that conductor is called A. That's just conductor A. And then I'm going to go around in the direction of the current, and I'm going to identify this one as conductor B, and this is conductor C. So I am guaranteed that the potential difference between the conductors A and C, which is maintained by this battery, it's going to be 10 volts. That's what batteries do. But let me show you a trick. What I'm going to do, I'm going to subtract the middle conductor, but then I'm going to add it back, and then I still have minus V sub C. Can you see that what I've done is I've taken the line before, and I've added 2 terms which actually cancel each other. So you can see that this is manifestly the same thing as the thing above. But if you group these things together, you can see something quite special. This right here is the voltage across resistor 1 all by itself. So I'm going to say that's the voltage across resistor 1. And this right here is the voltage across resistor 2. Can you see VB minus VC? VB is on the high side, right? The high potential side. And then I go down over the resistor to the next conductor there. And the difference is the voltage across R2. Do you see that? And all of this is 10 volts, like this. So what's interesting about this is the voltage across a resistor is equal to the current through the resistor times the resistance of that resistor. So this voltage right here is the current through resistor 1 multiplied by the resistance of resistor number 1 plus, so this one is all the details for resistor 2. But the current is all the same, right? When I go around here, and if I was to identify that this one was current 2 and this one was current 1, and they were different, if current 1 was bigger than current number 2, that means that coming into somewhere in here is more charge per time than what's leaving. And that's a no-no. Circuits don't let that happen. What circuits force to happen is that if the current only has one path around, then the current everywhere along the path has to have the same value. Or else you get stuttered current, which is okay. Like stuttering current is, is physical. But we're not going to have that. Along this single cycle, the current is simply just the same everywhere. So the current through resistor 2 is the same as the current through the wire labeled B, is the same as the current through resistor 1, is the same as the current through wire labeled A, is actually the same as the current that travels right through the battery. That is, the current is everywhere in the circuit at the same time, right? So if this is true, then I've got an update to my equation. I've got this 10 volts equals a common value of current multiplying the sum of the two resistances. And I'm going to call this the series resistance. Sometimes you might see this called the equivalent resistance. And this might be really similar. So our series it's just R1 plus R2, or R equivalent is R1 plus R2. This might remind you, right, of capacitor networks. But in capacitor networks, if you put two capacitances in series, do you remember that this is the same, right, equals an equivalent capacitance, where C equivalent is equal to C1 times C2 divided by C1 plus C2. There was this very strange way that the capacitances combined when capacitors were in series. But resistors, when they're in series, they add together. Okay, so, all right. So that's the series resistance. Now the next topic is, let's do an application, right? And we're going to do an application of the series resistance. And the application is associated with a model of a real battery. So let me tell you about a real battery. Like if you actually use a battery, so let me draw a picture that's meant to be a diagram of a real battery. So here is a real AA battery, right? And if you use it to, say, run a little light bulb, so this is meant to indicate the filament of a light bulb, so it's encased in glass. right, to protect the filament, keeps oxygen essentially away from it so your filament doesn't rust. Okay, so I have a circuit and this light bulb can emit light, right? It emits light, it gets warm, etc. But the other thing is, right, this is Joule heating. It's because of a power dissipated by a resistance, right? It's I squared times R. So it's the power dissipated. It's called Joule heating. It's the way you feel it is there's a warmth. But the thing is as your battery is doing this job, the truth is your battery is also getting warm, right? Same is true for the battery. So what this is implying is there's an internal resistance. So if you look at this circuit, this is a resistor, but also the battery. Not only does the battery provide this thing called the voltage, but it also is a physical thing, and it's got a resistance. So that's a lowercase r. And so if we want to model a battery, we're going to say that this battery, one way to model it is to give it what's called an internal resistance. So it's R sub internal, and then give it the voltage, the electric potential difference. And when people model batteries this way, they don't often call the voltage of the voltage V. They actually call it E. And E is for electromotive force, right? So EMF. It is not a force. The units of electromotive force are volts, actually, joules per coulomb. There's nothing Newton about this. I mean, the joule contains the Newton in a way, but it's not purely itself Newtons. EMF is purely voltage. It's volts, right? Okay, so we're going to take this battery. So here, I'm just going to call it little r, but it's an internal resistance. Here is the electromotive force part of it. And I'm going to consider the case of powering some sort of external load, right? So this is the power supply. In between these little circle terminals is the power supply, but the power supply has an internal resistance. And external to the power supply is some sort of device that I would like to cause to work, like a light bulb or a toaster or a cell phone battery or a motor, right? A little electric motor, like a dentist's drill or something like that. Doesn't really matter. But here's my circuit. It's actually got two resistors. So modeling an ideal battery with a simple load, right? This capital R is the load, some sort of motor or rechargeable battery or something. It simply is the same as two resistances in series with a battery, like an idealized source of voltage. So what you get essentially is an expression that looks like the following. If you solve for the current, right, all you would do is use Ohm's law. It would be the EMF divided by little r plus big R, like this. This would be the solution for what current flows. And the direction of the current, right, it goes this way through the battery. It goes from the low side up to the high side, and then it goes around and through and around like that. So this conventional current is flowing this way in the circuit. But here is the application aspect. So in and of itself, this is interesting, and you can, get some answers to problems. But let's think a little bit. What if I wanted to study the power dissipated by the load, or the power used at the load? How powerful is the energetic thing happening at the load. The way you calculate that is you take the current flowing through it, which is called I, you square it and multiply by the resistance of the load, right? That's how you calculate power. And what we're going to do is just put this in, see what we get. So I squared is just the square of this. So E squared over R plus R squared. And then it's multiplied by another factor of R on top. And here is the interesting thing. What value of R maximizes this power? So this is a maximization problem. For a fixed value of internal resistance, in a sense, you don't get to change the internal resistance of a battery, right? You just buy the battery from the store, and whatever materials it's made out of have resistivities and etc., and it's going to come with a fixed internal resistance. But what you do have choice over is what load you put that battery on. So for fixed R, maximize P. The way you do this with calculus is you take the derivative with respect to the thing that you imagine being able to make changes to or selecting amongst. So dp by dr, and for maximization, you set this to 0. If you were to graph a picture of this, what it will look like is this, right? It's kind of parabolic. So as a function of capital R, this is the power axis, and it goes like this. And there is a max value, right? That's going to maximize the power output, right? So if you take this derivative, you're going to have to take the derivative of this expression right up here. So it's sort of complicated looking, but the truth is it's actually quite easy, right? So let me show you a trick you can use. Because it is a quotient, right? You have to use the quotient rule for derivatives, but I'm not going to use the quotient rule. I'm just going to rewrite the power equation. So the power used up at that load R is equal to E squared, which is independent of capital R, and then multiplied R times little r plus big R raised to the minus 2, right? So it's to the square on the bottom, but that's the same thing as on the top with a negative 2 exponent. So E squared, right, the EMF squared, that's constant with respect to R. And so when you take the derivative, it gets skipped. So it's equal to, so that's going to just be a constant on the outside. And then the derivative, so the derivative of the first times the second plus the derivative of the second times the first, right? I'm going to use the quotient rule, not the quotient, product rule for derivatives. So the derivative of the first is just 1, so it's 1 times little r plus big R raised to the minus 2, plus the first times the derivative of the second. But the derivative of the second has the exponent, so the exponent comes down, right? It's a negative 2, and then you get r plus capital R. You have to reduce the exponent in the derivative, and then you multiply by the derivative of the inside, but the derivative of the inside with respect to capital R is just another factor of 1, and all of that is together. And we're setting all of this to 0. So what you can end up getting is if you go through the motions and solve for capital R, you're going to get the thing that maximizes the power is if you just use the same thing as the internal resistance. This is referred to as load matching. It's like the sweet spot of having a resistance that is not so big that you squeeze off the current, right? You don't want capital R in our circuit to be so big that the current is too small. If the current is too small, then the power is 0, right? But if R equals to 0, then you get sort of the opposite thing to happen. What happens is that the power actually kind of goes back down, right? So if you choose R too small, even though your current is increasing because you have less resistance overall in the circuit, this multiplication by the small r squeezes out the power too. So there's some magic position, magic choice of R that maximizes the power. And so what you do is you make sure your load, as an engineer, you make sure your motor has a load that matches the internal resistance of its power supply. And what you do is you get the most powerful transfer of energy from the battery to your little device, your little motor, right? So your motor can do the best possible job. And honestly, that's an engineering choice, right? And the way this engineer would solve this problem is with a calculus move, right? So these are all tools that make you rich if you know how to use them, or make your boss rich.